All right, welcome back, everybody. So in this video, in the previous video, we actually motivated what we're trying to study. We're trying to figure out how to work with optimization or minimization problems to solve questions from linear algebra. And in our first segment here, beyond the introduction, we need to figure out the context in which we're going to solve these problems. And this is going to be kind of a blend of linear algebra with multivariable calculus. And it's kind of interesting that we can do calculus, right? We can minimize functions of multiple variables without doing any calculus whatsoever, right? In fact, we're going to skirt around the calculus portion using principles from linear algebra and specifically from inner product spaces to make this work. Now, in order for us to get going, we need to hash out something fairly a minor point, but important nonetheless. And it's that we would like to recall we would like to figure out what the simplest functions are that we can try to minimize or maximize. And you might think, okay, the simplest functions we can deal with are linear functions or equations with linear components to them. And sure, yeah, that's exactly what we've been trying to do for the semester up until this point. Solve linear equations in a practical way. But for this problem, if we're trying to maximize or just optimize a linear equation, think about what a linear equation or the graph of a linear equation looks like. These guys are lines, and lines have no global extrema whatsoever. Okay, I mean, you might say, okay, these guys push off to plus or minus infinity, or they are just perfectly flat functions, right? They're constant functions. But the point is that generically, these guys have no no global extrema, let alone relative extrema. So linear equations are the simplest algebraic objects to study, but for optimization's sake, we need to move to the setting where these functions, where we have functions that have maxima or minima, and that can only happen when the curve is actually a curve and not a line. So this is why we have to deal with the next more complicated thing, and that would be a quadratic function. Okay, so given that multivariable calculus is not a prerequisite to this class, we need to describe what the process of, or what quadratic functions look like and how we might optimize them. So let's go back to a question that's familiar to everyone, right? Calc 2, right, is a prerequisite for the class, which means you had to go through Calc 1, where this question was posed, or that we kind of ad nauseum went through all the different ways, or a procedure for how to find all critical points, all maxima and minima of certain of functions. And we're going to do this specifically for the case where we have an arbitrary quadratic function, and notice that I put a 2, right? I doubled the coefficient on the linear term. We'll see why in a moment. But the point is that we can do this, right? We can use calculus to figure this out. Okay? If we compute the derivative of this function, we differentiate p, and we wind up with 2a x star plus 2b, and we set that derivative to 0, then that means that we have found all candidate local extrema. And because this is a parabola in general, right, the graph is a parabola, we have found the one and only critical point to this function. And in this case, x star is going to be minus b over a, right? If we didn't have the 2 sitting on this component here, then this 2 would be absent in the derivative, and we'd have minus b over 2a, right? And that might look familiar to scholars of the quadratic formula. But I digress. Calculus is going to give us a critical point, and we can go ahead and substitute that into the original function to figure out what the critical value is, provided we are actually dealing with a parabola and not killing off that first term so that we have a line instead. Okay, so that's why we need to make sure a is non-zero. Okay, so that's calculus, right? That's something we should all know. And specifically, if this coefficient in front of the parabola is positive, then we're going to have a minimum at the critical point rather than a maximum if a is negative. And now, what I'd like to do instead of calculus, let's see what this looks like from an algebraic point of view. Right? So again, this critical point comes out of kind of a different version of the quadratic formula. And the quadratic formula you get through completing the square. So let's go ahead and take this original function, this quadratic function here, and complete the square on it. Right, you can follow this algebra. I'm not going to step through the algebra. It's something you should know how to do at this point. Right, if you complete the square, then you will wind up with this expression. Right, this is the vertex form of a parabola. And notice where the minimum or maximum occurs is going to be at the vertex. So in particular, we can see that this is going to happen, like this guy is going to be smallest when I don't add any more positive terms to it. Right? This x plus b over a term is squared. So if this is anything but 0, then p is going to be greater, specifically if a is a positive number, then p is going to be greater than this c minus b squared over a. So that means that at the vertex, this function p is minimized, and this occurs when I kill off the square term, which happens at minus b over a, and that once again picks up a minimum value of c minus b squared over a. Okay, so this is what we need to generalize. Instead of using multivariable calculus, which is kind of not the point, we could either choose to go into multivariable calculus or we could choose to look more at the algebra. Since this is a class on linear algebra, we're going to focus on the algebra. We need to find a way to extend this process into multiple variables. So follow me over to the next page, and we'll see what this looks like. So for an arbitrary quadratic function, right, not a quadratic form, right, quadratic forms don't have these two terms in them. So be very cautious of the terminology. So an arbitrary quadratic function is going to take this form. And it looks scary, but take a look at the indices. If you really want to, break this down into a two-dimensional case to begin with. So you have what? K11 x squared plus 2. No, not 2, because we don't necessarily assume that's symmetric. Oh, shoot. 1, 2 will be an xy term. 2, 1 will be a yx term. K2, 2 will be a y squared term. We'll subtract off twice, and this will be an f term, so f1x minus 2f2y, and then plus a c, right? This is effectively the case where n is equal to 2, right? So this is how you should be reading these functions. Yeah, they are kind of scary, and notice that this first sum is actually a double sum, so do be careful. But the point is that this is just kind of a placeholder. This is what the abstract quadratic function is going to look like. The arbitrary quadratic function will look like this. So, a couple of thoughts, right? These Kij terms are now going to be in the original p function. P of x was ax squared plus 2bx plus c. Right? The a term is going to be associated with these Kij terms. So there are a lot of second degree terms, right? And we need to find a way to consolidate them into a single coefficient, so to speak. Same idea with these b's. These b's are going to be associated with the fi's. And the C's, well, there's just the one C here, and he associates with himself. So this is the relationship between what we had before and what we need now. And we can write this system in matrix form, believe it or not. Oh, you can totally believe it. It's a linear algebra class. If I say a matrix exists, oh, we're gonna play with it. So we can write this P function in the following form, and I suggest you kind of take a second, pause the video, and see what the connection is between this P function and oh, I overshot it, and these terms, right? Convince yourself that the right-hand side of this equation is exactly this downstairs. So again, pause the video and double check for yourself. Convince yourself that that's true. All right, and we're going to move on and say that without loss of generality, we can replace a non-symmetric matrix with its symmetric part, right? Without it's essentially just a change of variables. And this is not going to affect us too badly. We do have to be a little bit careful about what kinds of matrices we can change variables into. But the point is, we're going to assume that these Kij and Kji terms are the same, right? And that's just for simplicity's sake. We don't have to do this, but this is the vast majority of the time what we see in practice. We will set up symmetric matrices. And now comes the tricky part. Remember this P of x, ax squared plus 2bx plus c, right? We were looking for minima, and we said a greater than 0 is going to produce a minimum somewhere in this parabola. What does that mean now? What does a greater than 0 mean? Oh, and I'll point you in this direction. When we talk about this matrix, what should it mean for a matrix to be positive? Well, given what we did in chapter 3, talking about norms and positive definite matrices, inner products, and how they relate to positive definite matrices, this is exactly what we are going to do. We are going to make sure that we use positive definite matrices in order to make this a greater than 0 term, right, extend to this matrix setting. This is the natural way to extend this guy, right? This is exactly why we see x transpose kx show up in our system above. We are going to make sure that we use positive definite matrices in order to find minima, right? Minima will only exist if we have positive definite matrix coefficients. So, in general, we are going to try... Oh, wait, what happened? What happened? Did I have a question? There may have been a question around here. There was a question, but I have no idea what it was. The following theorem is what... Oh, what should this mean? Yeah. Yeah, what does this look like for quadratic functions? For a quadratic function. There's the question. That was the question right up there. You almost got away from me, but I found you. I got you. I got your number question. Okay. And the question is, what does this specifically? What does this minimization principle in linear algebra look like if we have multiple variables involved? If we have a multivariable function involved, right? And we've already answered a couple of preliminary questions. Right, that this is the setup that we need, and we need to use positive definite matrices. And the following theorem is going to tell us exactly what the minimization principle looks like. And specifically, if we have a positive definite matrix K, then this quadratic function P, right, from before we wrote it as x transpose kx minus 2f dot x plus c, this guy will have a unique minimum. So this guy, think in the n equals 2 case again, we're going to have not a quadratic, or not a parabola, but instead we're going to have a paraboloid, right? So we need to make sure that in each of our coordinate directions we are facing up. We are concave up in every one of our fundamental coordinate directions. Right, that's what positive definite is going to do for us. This is opposed to, say, a saddle, where there is one direction that is face up, but there is another one entirely that is going down. Right, so we go up in this direction, but down in that direction. And positive definite is making sure that we get ups in all directions. Okay, or we get concave up in all directions. And that minimum, right, the unique minimum that shows up for this solution, or for this quadratic function, should look like something that was familiar before, where x star looked like minus b over a. Well, that sure looks like a inverse times b. All right. And the minus sign only showed up because this was a plus, so if we flip this to a minus sign, then these become pluses, that becomes a plus, and we're all set here. Okay? So again, we are just translating this into a higher dimension. And the minimum value is going to be exactly what happens when you plug in this x star into this equation, or yeah, into this function. And this function will spit out that minimum value. Let's prove it real quick. Right. So again, we are completing the square in a higher dimension, right? In a more abstract, or yeah, higher dimensional setting. So this one, I actually encourage you to follow the work not from here down, but rather backwards. Figure out where you want it to go, and then trace it back up. Right? Completing the square in a higher dimension is a little bit trickier, so try to follow from the bottom up rather than the top down. Right? And there's one step in here that requires the symmetry in the matrix K. Right? This is one of the reasons why we have to appeal to symmetric matrices, or force symmetric matrices to be the object to work with. Now, once we get to this point, if we were dealing with a solution here, right, I could rewrite this as kx star equals f, which is exactly what I'm doing right here. Right, so if I did have a solution, right, if I did use that particular solution, then notice that this term here, right, this is behaving much like the ax plus b over a term squared from before. And when notice that this guy is always greater than or equal to 0, because K is a positive matrix, right? It doesn't even have to be positive definite, but the fact is that this guy is a positive matrix. And that means that this red circle term cannot be negative, which means if I were to find where this guy zeroes out, then what remains is going to be the minimum value of the function. All right, so let's see if we can't finish this out. So the only way that this guy is zeroed out is if I'm on this x star term. And that's by the definiteness of K. So there is a minimizer, and that minimizer has to be this K inverse times F. Right? K inverse definitely exists because K is a definite matrix. There's only one way to get the zero vector out of it, right? So the kernel is trivial in that sense, right? And once we get to that point, once we kill off the quadratic term, what remains is the minimum value of the function, right? Whew. All right. Not too bad, I don't think. Right, and we'll go through one quick example here, and I think, yeah, so 2 more pages on the notes. So let me just show you what this looks like in practice. So let's say we are going to minimize this quadratic function, right? So if you were paying attention to the terminology from before, these are the k, f, and c values that we need to take, or that will show up. Notice how the -4 here is actually split among two components of the K matrix, right? This is reflecting that reflecting the fact that we have an XY term and a YX term, right? And we are technically treating them differently from the algebraic point of view. But if I have those matrix, vector, and C values, or scalar shifts, then the trace being positive and the determinant being positive for a 2x2 matrix is enough for us to show that K is a positive definite matrix. So, because I have the setup with a positive definite matrix, there is a minimum for this function, and the minimizer is x star, which is given by this K inverse times F. And K inverse you can compute easily enough, right? So I challenge you to remember how to remember the formula for a 2x2 matrix inverse. Right, it's going to involve interchanging some entries of the matrix, negating others, and then dividing by a determinant. That should sound familiar at this point. And we're going to multiply that into the F vector, 1 by -2, and that'll pick up this vector, -3 by -7. So supposedly, this is the location, the location in the xy plane that minimizes this function P upstairs. Okay. Shouldn't be too bad yet. And following the theorem, K minus Fx star is going to get us the minimum value. In this case, it's going to be a -8. All right. And if you really want to check this, you could go into MATLAB and kind of validate or plot what this guy is going to look like. But we're already running a little long in this video, so I'll skip it for now. The theorem then says that this is the unique global minimum. Right? So that's how it would look for some arbitrary quadratic form. And these guys can be arbitrarily, they can have an arbitrarily high number of variables to work with. So we would like to be able to do this in a computer so we don't have to do this process by hand every single time. So the only real algebra for this setup now comes from solving kx star equals f. So this is again an ax equals b setup. Oh shoot, that's the eraser. This is again an ax equals b setup. So you can see why we want to keep trying to find quick ways of solving this system. But we can employ whatever techniques we want to solve, since computing K inverse is usually pretty expensive. So what we can do here maybe is do like a QR factorization, maybe do an LU factorization. But the point is that we have methods that can solve this a little more quickly than Gaussian elimination. Right, and we can check this. We can check that the theorem is true by using multivariable calculus. If you want, you can actually go ahead and compute the gradient for this guy. Well, grad P, what is that going to be? 10x minus 4y and then plus 2. And then we'll have, what, a minus 4x plus 2y minus 4. And you set that guy to 0, and you can see that you will get exactly that solution downstairs. Right, just plug in x equals -3 and y equals -7. You're going to see exactly the right thing. You're going to see exactly the thing that kills off this gradient vector. So yes, multivariable calculus can be used, but remember, we're doing this from the algebraic point of view. But all that the gradient will be able to compute for you, just like in the single variable calculus sense, it's only going to be able to show you that this is a local minimum or local minimizer. But what the theorem that we have for the linear algebra case shows that this is a global minimizer. So if the function is nice enough, we can actually show that we have a global minimizer for this equation, and that is what we want. Right? This is a more powerful statement than saying that we just have a local minimizer. Now, so notice the caveat I said there was if the function was nice enough. The last thing I'll say here is that there is a version of this theorem if k is semi-definite. It still needs to be positive, but it still works if there's a semi-definite case. But there's a little bit extra that we have to do here. We have to guarantee that f is in the image of this k matrix, right? It was guaranteed before since k was invertible. But if we got rid of the definiteness, right, we go to semi-definiteness, then we may not have a solution. We may not have a solution to kx equals f. So we need to make sure that f is in the image of k, and if it is, then any solution, right, in fact there's going to be infinitely many now since the kernel is non-trivial, any solution to kx star equals f is going to be a global minimizer for this function down here. Right? Same proof works as before, but we get infinitely many solutions to the kx star equals f bit. So again, do be careful in employing an inverse, especially if it doesn't exist. Right? So we'll go ahead and end this video now. That should take us to the end of 5.2. And I will see you next time so we can start talking about closest point solutions, or nearest neighbor, or not nearest neighbor, closest point solutions, or start working toward least squares solutions.